Welcome to this particular lecture on the scattering theory. And in this particular lecture, we will look at the Lippmann-Schwinger equation, which is the very important equation to calculate the scattering amplitude. Because scattering amplitude is one of the important quantity in the scattering theory. Because I had told you in the last lecture that if you have the expression for scattering theory, then you can calculate the differential cross section, and which is the quantity that we are looking for in the experiments. So in fact, calculating scattering experiment is sorry scattering amplitude is the goal of the whole scattering theory, and this is what we are going to start in this particular lecture, right? So we will see one of the method to calculate the scattering amplitude, the expression, mathematical expression for scattering amplitude, and that is just to get the Lippmann-Schwinger equation, and from there you can get the mathematical expression for the scattering amplitude. So in this particular lecture, we will derive, you can say, or you will see how we can get the Lippmann-Schwinger equation from the differential equation, the Schrodinger differential equation. So in a sense, this lecture is just to convert the differential equation, the Schrodinger differential equation, to some integral equation, which will be called as Lippmann-Schwinger equation. So it is just a conversion from differential equation to integral equation. The differential equation is called the Schrodinger equation, and that integral equation that we will calculate in this particular lecture will be called as Lippmann-Schwinger equation. So let me show you the arguments, the derivation for that particular equation. So what we did till now is that we have just seen that we have to solve this particular differential equation, which is the Schrodinger equation in center of mass frame, right? We have to solve this particular equation where this V of R is the scattering potential, and I have discussed about this in detail in the last lectures, right? I have also shown that this particular equation can be written in this particular form, right? Where I have just assumed this particular term as U of R, but let me write it this way in this particular lecture, right? So this is the equation that we are looking the solution for, right? So this is the ultimate goal for us to calculate the solution of this particular equation. So what we will do is that we will use the Green's function technique. So we will use the Green's function technique uh, to solve this particular differential equation, to solve the above differential equation. So before going deep into this particular derivation, let me just introduce you what the Green's functions are, right? So it may be that you have studied about the Green's function already, but let me give you the glimpse of the Green's function technique. So what Green's function technique says that if you have some non-homogeneous differential equation, so if you have the non-homogeneous linear differential equation, so linear differential equation, right, of the form L acting on some function y of x giving you some q of x. So if you have this kind of equation, right, this is non-homogeneous equation. Why it is non-homogeneous? Because the right hand side is non-zero. If the right hand side of this equation is zero, then the equation will be homogeneous equation. So you must have studied the theory for differential equation, and in that you have studied homogeneous, non-homogeneous equations. So if the equation is non-homogeneous, right, so what this Green's function technique claim is that we can write then we can write the solution, which is x y of x, right? The solution of this particular differential equation, which is y of x, we can write in terms of Green's function as the integration of Green's function into the function on the right hand side dx, right? This is the claim of the Green's function technique, where this g of x is Green's function. So it is Green's function, a mathematical function. You don't have to take it that serious, you just have to assume it as a mathematical function of x, and this Green's function can be calculated by this particular equation, right? So this L has to act on Green's function, will give you the direct delta function. So this is what the Green's function technique is, right? If you have some non-homogeneous differential equation, then according to this particular technique, it claims that the solution can be written in this particular integral, right, where this g of x is called Green's function, and this Green's function is given by this particular equation, right, where this delta x is direct function, so direct delta function. You all know about it, right? So this is what the technique is, and these are what the claims are, and we will use this particular technique to solve this particular equation, which is the equation for the scattering problem that we are looking for. So now let me show you how we will use this same technique to get the solution of this particular equation, right? So before that, right, before that, we know for, or you can say, the particles, for the particles, for the particles far from, far from the potential, scattering potential. So far from the scattering potential, we know that V of x is 0, right? So let me say V of r, because we are doing scattering in the 3 dimension, so not the 1 dimension. So we know that if the particles are far from the potential, then V of r is 0, right? If V of r is 0 at that point, then we know that this particular side will be 0, because this V of r is 0. The equation will be like Laplacian plus k square into psi of r is equal to 0, right? And this is the Schrodinger equation for free particle, right? So it is Schrodinger equation for free particle. We have seen this equation in the last lectures, right? And we know that if particle is free, then we can write this wave function for that particle as plane wave. So we have seen all these things. K naught dot r. So this is the solution when the particles are very far from the scattering potential, right? So this is when the particles are far from the potential. Now what we want is the solution for this particular equation, where we do not require this particular V of r as 0, right? So according to this particular technique, right, so as for Green's function technique, Green's function technique, what this technique claims is that the solution of this particular non-homogeneous equation can be written as, so solution of this particular equation can be written as integration of Green's function, and we will use arguments as r minus r dash, right? What are r and r dash? So it is just, you have this particular target, and there it is detector, right? So these are detectors and these are particles, so these are targets, and we have just some imaginary origin, and what we are doing is that we are observing some point source on the target which is scattering the particle, right? And its position is r dash, and position of detector from this observation point is r, and this particular vector which is in between the scattering point source and the detector, which will be r dash, sorry, r minus r dash, and that's why we are taking the argument of the Green's function as r minus r dash, right, into the where it is, so yes, into the function on the right hand side, right, function on the right hand side. So the function on the right hand side is this, so it is just 2 mu over h cross into v of r, right, into psi of r into dr or d cube r, because we are calculating in 3 dimension. One more thing is that we are just changing the variables, right? So we are just changing the variables to calculate the integration because of this particular source, right? So this is the claim of the Green's function technique. So let me write it in this way, in this particular way. So it is just 2 mu over h cross square into integration of g of r minus r dash into v of r dash into psi of r dash into d cube r dash. So this is the claim or claimed solution of this particular non-homogeneous equation according to the Green's function technique, and where This function g of r minus r dash is called Green's function, and this function is given by, as we know that this Green's function has to be given by this particular type of equation. So here this function will be given by Laplacian plus k square into Green's function r minus r dash is equal to del cube r minus r dash. So these are the two big claims, right? So these are the claims according to the Green's function technique. Now, in fact, we will show that this particular equation is in fact the solution of this particular equation, right? So now let me show you why this particular assumption is right, or this technique, Green's function technique, is appropriate to solve this particular differential equation. What you have to do is that you just have to operate this particular operator on equation number 2, right? So you just have to operate. So we have to operate. We have to operate operator, which is Laplacian plus k square on equation number 2, right? So it will be like operator, Laplacian operator plus k square into 2 mu over h cross square integration of g of r minus r dash v of r dash into psi of r dash d cube r dash. Now let me calculate the expression. So this Laplacian operator is with respect to r dash, right? So it will just act, sorry, with respect to r, so it will just act on this Green's function. So let me just operate this particular operator inside. So it will be 2 mu over h square integration. It will be Laplacian plus k square into the Green's function into v of r dash psi of r dash d cube r dash, right? Now just look at this particular expression. This operator is acting on Green's function, and we know by definition that if this operator is acting on Green's function, it will give the Dirac delta function. So it will be just 2 mu over h cross square into the delta r minus r dash into this v of r dash into psi of r dash into d cube r dash. And you know by the property of the Dirac delta function that this particular integral will be, right, it will be just 2 mu over h cross into this particular expression, which is v of r dash into psi of r dash, right? So this is what the expression is, and if you just look at this, this is just the right hand side of this particular equation. So what we did, we have assumed psi of this particular equation as the solution of equation number 1, and what we did, we just have operated this operator on this particular equation, and we got the right hand side. So what it means is that yes, in fact, this particular equation is the solution of equation number 1, right? So the claim this particular technique does is in fact right, and we can say, or we can write this particular equation as as the solution of this particular equation. So this is what we did till now. So what we, let me just conclude what we did. First of all, we have converted this particular differential equation in this term, and then by using the Green's function technique, we have said that psi of r can be written in this particular form, where g of r is the Green's function, which is given by this particular equation, and we have shown that in fact this equation is the solution of this particular equation, and it is right to assume the solution of equation number 1 in this particular form, and this is what we have did till now. Just let me write these important equations on this particular side, right? So this psi of r is 2 mu over h cross square integration g of r minus r dash v of r dash psi of r dash into d cube r dash, and this equation Laplacian plus k square into Green's function, which is g of r minus r dash, which is giving the delta function delta cube r minus r dash. So these are the three important equations till now, and we got this particular claim is just by using the Green's function technique. If somehow we can calculate this function, right? If by using some technique we are able to calculate this particular function, which is Green's function, then we just have to put that function in this particular equation and we will get the solution, right? So this is that simple now, right? But again, this is not that simple as I'm saying, but we just have to calculate the value of this particular Green's function. So now the thing is, we are going to calculate the value of Green's function, and once we will calculate the value of Green's function, we will put it in this particular equation number 2. Let me write it, equation number 2. This is equation number 3, and that equation, after putting the value of G, will be Lippmann-Schwinger equation. So now we just have to calculate the value of this particular G of R minus R dash. How we will calculate the value of this particular G? So to calculate the value of Green's function, we will this is again the mathematical technique, right? We will write the Green's function, which is this function, in terms of its Fourier transform. So we will write the Green's function in terms of, or in its Fourier representation. So you all have studied the Fourier representation in your M.Sc first sem. So we just can write this Green's function, which is G of R minus R dash, as 1 over 2 pi cube integration, right? G of, let me write it, e to the power iota q dot, q is the different, this is R, which is one of the variable, and q is the second variable, into R minus R dash, right? And so it is just R minus R dash into the Fourier transform of this particular function, which is G bar of q into d cube q. So this is the Fourier transform of the Green's function, right? And we will also write the this particular delta function in terms of its Fourier transform. So, and delta function, which is del cube R minus R dash, we are writing it also in terms of its Fourier transform. So you can check in some of the books that the Fourier transform of this particular function will be like e to the power iota q dot R minus R dash d cube, right? So these are the Fourier transforms of these two important functions, and this is the starting point to calculate the Green's function for this particular equation. You just have to write initially the Green's function and delta function in their Fourier transform form, and we will use these two functions to calculate this Green's function, sorry, the Fourier transform of Green's function. Now what we will do is that we will put these two values in equation number 3, right? So putting, right, these Fourier transforms in equation number 3. So equation number 3 is that, so you just have to put these two values in this particular equation. So it will be like Laplacian plus k square into the Green's function, and Green's function is in this particular form, so it will be 1 over 2 pi cube into e to the power iota q dot R minus R dash into G bar of q d cube q, which is the Fourier transform of the Green's function, right? On the right hand side, this delta function, you just have to replace it with its Fourier transform. So it will be like 1 over 2 pi cube into e to the power iota q dot R minus R dash d cube. So this will be the equation. Now you just have to operate these operators inside, right? So you just have to operate these operators inside. It will be like, so this particular factor will cancel out, and this operator is with respect to R only, so it will be operated on this particular function, and it will not be operated on this function. So it will be like integration Laplacian plus k square into e to the power iota q dot R minus r dash and into, so it is just that this operator will act on this particular value, and it will be g into q d cube q will be equal to e to the power iota q minus r dash d cube q. So this is the equation. Now you just have to operate on this particular operator on this particular state, and what it will be like, it will be just, you just, it is just a particular value, so it will not be operated. It is just this particular operator will act on this particular function, and this is like to differentiate this particular function two times, and if you will do that calculation you will get minus q square, right? So you just have to operate this particular operator on this particular function for two times, and you will get minus q square. So you can do this particular calculation. It is just simple calculation, plus k square into the same function iota q dot r minus r dash g bar q d cube q is equal to e to the power iota q dot r minus r dash d cube q. So this is the equation. Now you just can write this equation as, let me write it like this. So let me write there. So what you can do, you just have to write it in this particular way. You can take this function here and just rearrange these functions. So it will be like k square minus q square into g bar q into e to the power iota q dot r minus r dash into d cube q, giving e to the power iota. It is just same. I'm not repeating it again and again, so you can, you know it very well. So this is the equation. This will be the equation. Now these two integrations are same, but you just know, you just can see that on the right hand side there is just integration of this exponential term, which is exactly same on the left hand side too. But here in this, in the product or multiplication of this particular exponential is just one, and if these two integrations are equal in magnitude, then the integrand, which is this particular value, has to be equal to the integrand of this particular exponent. So we can say that if these two integrations are equal, then the value of this particular quantity has to be 1, right? And from this particular equation, this g of q, which is just the transformation of the Fourier transform of the Green's function, so it will be 1 over k square minus q square, so very important quantity. And we can write Green's function now as g of r minus r dash as 1 over 2 pi cube into what it was, like e to the power iota q dot r minus r dash into this particular function, which means this will be in the numerator, sorry, denominator, which is k minus q square into d cube q. So this is the new Green's function after putting the value of this particular transform, the Fourier transform of the Green's function. So this is the calculation till now, right? Now we have to solve this particular integration to get the value of this Green's function, because then we will put that value in this particular equation, which will be the Lippmann-Schwinger equation. So let me do the further calculation. Let me write it here. So what you can do is that this is integration in the q space, right? So this is the volume element in the spherical coordinate system, and I have told you in one of the lectures how we will calculate the volume element in the spherical coordinate system. So we just have to replace this particular volume element in spherical coordinate system. So we can write this particular integral as, so g of r minus r dash will be equal to 1 over 2 pi cube integration of e to the power iota q dot r minus r dash over k square minus q square into the volume element, which is q square sine theta dq, d theta, and d phi. So this is just the volume element in the spherical coordinate system. So if you don't know, you just have to go to that particular lecture where I have explained why the volume element will be this much. So you just have to take these particular integrations, and this is just a volume integral. So this is not the single integral; it is the triple integral. You just have to separate it out. So you can write it like g of r minus r dash equal to 1 over 2 pi cube into the q part. So it will be just like q square over k square minus q square into dq, right? And the integration on dq is within limit 0 to infinity, right? Into the integration over e to the power iota. If you just take the dot product in between these two quantity, it will be q into the mod of r minus r dash into cos theta, right? The angle between q and r minus r dash into sine theta d theta, and the limit in the spherical coordinate system of on theta is from 0 to pi into integration over d phi from 0 to 2 pi, right? So this is what this integration will be, right? So now just solve it step by step. We know that the integration of this particular term is just 2 pi, right? These are the basic mathematics. I'm not going to just show you everything in detail, right? So let me write it. So the integration of this is 2 pi, and let me calculate the integration of this particular term. So the integration of iota q r mod of r minus r dash into cos theta into sine theta d theta from 0 to pi. So this integration you can solve just by putting cos theta equal to x, and you know it will be sine minus sine theta d theta is equal to dx, just the basic mathematics that you have studied in your class 12th. So it will be like and the limit will be from plus 1 to minus 1, because cos of 0 is 1 and cos of pi is minus 1, so the limit will be from 1 to minus 1, and this will be e to the power iota q mod of e minus e sorry e mi r minus r dash into x. It will be minus of dx. Okay, because of this minus you can flip the limits, so it will be like minus 1 to plus 1, and it is just e to the power iota q mod of r minus r dash into x into dx, and this is just the basic exponential integral, and you just can write it like this 1 over iota. You all must know how to calculate this kind of integration, so I'm not going into the details, right? So it will be like the integration of this particular term is just the same over the differentiation of this particular term. So this is what I did, and integration, and in this particular integral we will put the limits. So it will be like e to the power iota q mod of r minus r dash minus e to the power minus iota q mod of r minus r dash, and this will be the integration, right? Now you just have to put this particular value at this place and put 2 pi for this particular expression, and it will be like, let me rub it. So it will be like 2 pi from there, right? So it will be 2 pi over 2 pi cube integration. The integration of this particular term is this, so let me write it q square over k square minus q square, and it is from 0 to pi, and this particular term which will be 1 over iota q r minus r dash into e to the power iota q r minus r dash minus e to the power minus iota q r minus r dash and into dq, right? So this is the expression that we have to solve. Now it will cancel to 1 of the power, and it will be like 1 over 4 pi square into this particular term which is 1 over q, and because integration is with respect to q, so this particular term will be out. So it will be mod of r minus r dash. This q will cancel to this particular power, and it will be like q over k square minus q square into e to the power iota q r minus r dash. This is mod minus e to the power minus iota q mod r minus r dash. So it is just a mathematics, right? You must have to know how to solve this particular integral. Let me write this particular expression here, because it is this thing what we have to solve. Pi square iota r minus r dash into integration from 0 to infinity. It is q over k square minus q square into e to the power iota q mod of r minus r dash into dq minus integration. Let me just take it as common from 0 to infinity, and it is q over k square minus q square into this particular term, which is e to the power minus iota q r minus r dash dq. So this is what we have to solve now to get the value of Green's function. So this is what we are doing to get the value of Green's function. So this is just the Green's function that we are calculating. Now what we can do, you can just apply this mathematical trick to just move a little bit further. You can add this particular term, so you can add from minus infinity to plus infinity the same integrals k square minus q square e to the power iota r minus r dash dq. So you have just added this particular term, so you have to subtract this particular term as well. So first let me write this term from 0 to infinity q over k square minus q square e to the power iota q r minus r dash dq. So what you did, you just have added this particular term, so you have to subtract this term. So we have to subtract this term q over k square minus q square, and it is from minus infinity to 0 e to the power iota q r minus r dash and dq. And there is this one term which is minus integration of q over k square minus q square e to the power minus iota q r minus r dash dq from 0 to infinity. So this is the whole thing that we have to do. Now you just can club these two terms, right? You can take these two terms as common from limit minus infinity to plus infinity. So it will be like 1 over 4 pi iota r minus r dash, and it is minus infinity to plus infinity the term q over q k square minus q square into e to the power iota q r minus r dash into dq. Right, again these are the mathematical tricks to get some solution. Now we have these two terms, and you just have to look at them a little seriously. Now you just have to replace, right? You just have to put, or you just have to replace q as minus q in this particular term, right? So let me just write replace q to minus q in this particular term, right? So what will happen, it will be minus q, right? It is minus q square, so again the q square, so it is minus q, and it will be minus q there, right? So it is the exponential where there is this minus q, and it will again be the exponential where this particular term will be same, right? So what it will be by doing that, so let me write this replace q minus q in q over k square minus q square e to the power iota q mod r minus r dash dq. So it will be it is just, let me write it here, it will be like minus q over k square minus q square, and it will be like q e to the power minus iota q into r minus r dash, this is more. And when you will replace q with minus q, then this dq will be replaced with minus dq, so it will be like minus dq, right? And this is limit from minus infinity to plus infinity. But when you will replace q with minus q, the limit will also change from minus to plus, so it is minus infinity, so it will be changed to plus infinity, and it is plus 0, so it will be changed minus 0. So plus 0 minus 0 is same, but this infinity will be plus infinity because of this particular variable change. So this will be from plus infinity to 0, and this particular term, this minus and this minus will cancel out. So this is the second term, right? This particular term, the third term is just as it is, so write it like minus from 0 to infinity q over k square minus q square a to the power minus iota q r minus r dash dq. So this is what the expression is, right? This is what the expression is. Now if you can see, this term is just exactly equal and opposite to this particular term. Why? Because this minus will cancel to this particular minus, right? And if you just flip the limit of this particular integral, right, so it will be in the next line, you if you just want to write, it will be minus 0 to infinity, this minus and this minus will be plus, and this particular term is exactly equal to this particular term but opposite in sign, so these terms will cancel out and this will be the only result, right? So let me write the result directly. So the final expression for the Green's function is 1 over 4 pi square, it is pi square iota r minus r dash into integration from minus infinity to plus infinity of q over k square minus q square into e to the power iota q r minus r dash dq. So this is the expression that now we have to solve. Now this is the expression that we have to solve finally to get the expression for Green's function, and we can solve this particular expression by using the contour integration method, right? You all have studied about this contour integration in the complex integrals, right? So you have studied that in your mathematical physics course. So we will use complex integration technique to get the solution of this particular equation, right? To get the solution of our equation. And what you know just by looking at this particular equation is that this particular function, which is this function, has two poles, right? Right? How do we calculate pole? We just have to equate the denominator equal to 0. So we have to equate this equal to 0, and we know that the value of q will be plus minus k, and at these particular two values this denominator will be 0. So this particular integral has poles on at the values plus k and minus k, and we have to calculate the residues at these particular values. And then what we have to do, by we can get the integral of this particular expression as 2 pi iota into the sum of residues, right? So this is what the technique that we will use. And how do we calculate the residue of this particular term? So what we will do is that, so let the function, this particular function is, let me write it as function of z as z into e to the power iota z into r minus r dash divided by k square minus z square. This is what the function is, and the poles are at plus k and minus k. So the residue will be like you must have known it already, so I'll just directly calculate it. So residue is at plus k and minus k, so let me calculate for plus k. So it will be z tending to k, right? K minus z into f of z. This is the way to calculate the residue. So it is just to calculate this particular limit. So it will be limit z tending to k, which is k minus z into f of z. F of z is this particular function, which is z into exponential of iota z r minus r dash over this particular function, which is k square minus z square, and we can write it like k minus z into k plus z. K minus z will cancel to k minus z, and you just have to put the value uh, for z as k, and you will have the residue as uh, you just have to put k on at the place of z, so it will be k into e to the power iota k into r minus r dash divided by, it is k plus k, and it will be like this will be 2k, and this is just k, so it will be 1 over 2, so it is just 1 over 2 e to the power iota k r minus r dash. So this is what the residue is, and we know that this particular integral is 2 pi iota into residue, right, the sum of residues, and at k this is just one residue, and that's why the Green's function for plus k, right, for plus k will be this particular term, which is 1 over 4 pi square into iota into r minus r dash, right, into the this particular integral, which is 2 pi iota into the residue, which is just this term. It is just half of e to the power iota k r minus r dash. This 2 will cancel to this particular 2, pi will cancel to 1 of the power, and iota will cancel to iota, and the value for of g, which is the Green's function for plus k, will be r minus r dash, which will be equal to uh, it is e to the power, or we can say 1 over 4 pi e to the power iota k r minus r dash divided by r minus r dash. So this is a very important expression if k is plus 5, oh sorry, plus 1, and similarly you can calculate the value of Green's function for minus k, and it will be 1 over 4 pi e to the power minus iota k r minus r dash 1, sorry, over r minus r dash, and this these are the expressions that we are doing the whole derivation for. So we got the value of Green's function for plus k and minus k, right? This is the expression that we will not use initially, right? Even in the scattering theory that we will do, we will not use this particular expression, because this expression is corresponding to the incoming spherical waves, right, which we are assuming not to happen there in the scattering. So we will use this particular expression to get the scattering amplitudes. We will use this particular expression, but not this expression, but because this expression is corresponding to the outgoing spherically symmetric waves, right? So we will use this particular expression. Now what we have to do, let me just write the solution which we have assumed. So this is just to get the value of Green's function, right? But the main aim is to get the value of a scattered wave function. So the solution of non-homogeneous equation, which was the equation like Laplacian plus k square into psi of r is equal to 2 mu over h cross v of x, or sorry, v of r psi of r. This was the initial equation, and we were writing the solution for this particular equation. And by using Green's technique, we have claimed that the solution will be like 2 mu over h square into the Green's function, right? The Green's function into v of r dash psi of r dash into d cube r dash. This was the assumed solution, and we have calculated the value of the Green's function. So let me write this solution, right, by just putting this value of Green's function in this particular equation. So it will be like it is just 1 over 4 pi into e to the power iota k r minus r dash over r minus r dash into v of r dash psi of r dash into d cube r dash. So this is the solution that we were looking for, right? But this is just the solution for scattered wave. The general solution, right? But the general solution of, let me say, this particular equation as equation 1. So the general solution of equation 1, which was the main equation that we are trying to solve, is, so let me, because this is just uh, psi of r, and we can write it like incident, the sum of incident wave plus the sum of scattered wave, right? So this particular solution is the scattered waves, and the incident waves, we already know that incident waves are the plane waves. So in general we can write the solution of this particular equation as psi of r as the phi incident, right? We know that these phi incidents are the plane waves, plus this particular expression, which is 2 mu over h cross square into 1 over 4 pi e to the power iota k r minus r dash divided by r minus r dash v of r dash into psi of r dash d cube r dash is the equation that we were looking for. There will be some this minus. I don't know. I think leave it somewhere. So you just have to make sure that it will be minus, right? So it has to be minus. But this is the final solution of this particular differential equation, and this equation is called Lippmann-Schwinger integral equation. So this is the equation which is called Lippmann-Schwinger equation. Lippmann-Schwinger integral equation, right? So if you just notice it, we are calculating the value of psi of r, but you have psi of r in the integral sign as well, right? So if you have this kind of equation where the quantity that we are looking for is also in the integration, then it is not that easy to solve this particular equation, right? But this type of equation are called integral equations, and this is the equation which is called the Lippmann-Schwinger equation, right? So how do we get this particular equation? We got this particular equation by solving this differential equation, which is this Schrodinger equation, by applying Green's function technique, then calculating the Green's function itself. So most of the calculation that we did is just to calculate the Green's function, and finally, when we got Green's function, we have written down the solution for the outgoing waves, right? And the general solution of this particular differential equation is this equation, which is called the Lippmann-Schwinger equation. Now, in the coming lectures, we will solve this particular equation by applying the Born approximation, and also we will see that how we can uh, take the asymptotic solution of this particular equation, right? Which will be which will convert it in the more familiar form. So all the calculation, the remaining calculation, we will do in the next coming lecture. So this is very hectic calculation, I know, but this is what you have to do to get this particular equation. You must know each and every step. How do we integrate it, right? How do we used the Green's function technique and all, right? Because that is what the hectic process is, and this is the final goal, is just to calculate the Lippmann-Schwinger equation in this particular derivation. So thank you so much.